Section 5.7 talks about one of the most beautiful aspects of integration theory that we'll encounter in this semester, and that's the idea of change of variables in multiple integrals. You probably won't be surprised to learn that when you're doing use substitution or trig substitution back in Calc 2, that idea generalizes to two and to double and triple integrals, 2 and 3 dimensions, and in fact it generalizes to even higher dimensional integrals. What we're going to talk about in this section today is at least we're going to get a glimpse of sort of the deeper mathematics behind change of variables in multiple integration. The big goals are for you to understand what a transformation is and to understand how a transformation takes a set in the domain and maybe morphs it into a set in the codomain or the range of the function. Then we'll learn about the Jacobian and how to compute the Jacobian. We have two examples of Jacobians already at our disposal in the context of polar/cylindrical coordinates and spherical coordinates. And we'll talk about that in a minute. And then last, sort of a skills-based item is to be able to evaluate double and triple integrals using a change of variables. Why do change of variables? The same reason that we did use substitution or trig substitution back in Calc 2. It's to make a really hard integral easy. And change of variables in multiple integration serves exactly the same purpose. So there's a bit of a summary here. Oops, let me go back to my notes here and let's do a bit of a discussion of the big ideas first of all. So this is a beautiful theory. The R that we encountered when we convert Cartesian integrals to polar integrals or cylindrical integrals, and the rho squared sine phi that we encountered when we converted Cartesian integrals to spherical integrals. These are examples of what are called Jacobians. And what they do is they correct the area element dA or the volume element dV according to the change of variables. So it turns out that polar coordinates, cylindrical coordinates, spherical coordinates are all examples of the kinds of transformations that we're going to talk about in this section. And the R of polar coordinates and the rho squared sine phi of spherical coordinates are these corrective factors that fix dA or dV under the change of variables. Change of variables is one of the most beautiful features or aspects of integration theory, and a lot of what we're talking about today wasn't really fully understood until the late 19th, early 20th century. So it's a relatively new piece of mathematics for you. Let me back up a little bit and provide a bit of context. We have great tools at our disposal for visualizing functions of a single variable, right? Those functions that you studied in Calc 1 and Calc 2. When I say f of x equals x squared, that evokes for you some geometric picture, right? A parabola. And it's so tightly woven together with the function f of x equals x squared that they're almost inseparable in our minds. Similarly, probably to a lesser extent, but in Calc 3 we learned that some functions, like a function of two variables, x squared plus y squared, can also be rendered geometrically as a paraboloid, right? A parabola, sort of a three-dimensional parabola or a bowl opening upward. And we learned a whole bunch of other kinds of shapes when we did quadric surfaces. Sadly for us, those are the only two kinds of functions that we can really visualize in this way. Most functions are not easily visualizable. What do I mean by most functions? Think about a function that takes a point in two-dimensional space over here and maps it or sends it to a point in two-dimensional space over here. How are we supposed to visualize that, right? If a function has its domain in R2 and its range in R2, we can't plot that as a graph, we can't plot that as a surface, we just have to imagine what's happening. But one tool that we do have at our disposal to help us visualize such functions is to take subsets of the domain of f, familiar subsets like squares and rectangles and circles and ellipses, and we take all the points in the square and we plug them into f, and we look at all the points that come out of that process over here in the range of f, and we're going to see that this nice simple square in the domain gets kind of twisted and morphed in certain ways when I plug all the points into f and I look at the result in the range. That's about the only way we have for really understanding the action of a function of two variables to two variables. Similarly, if we have a function of three variables that whose range is also three variables, we can take a blob, some kind of familiar blob like a cube or a sphere, and we can take all the points in that sphere, put them into f, and see what the result looks like in the range, also called the codomain, or is related to the codomain. So if I say codomain, I kind of mean range. There's a slight difference. So we could imagine, for example, a sphere. We put it into this function f, and over here it turns into an ellipse or a torus or some other kind of exotic three-dimensional set. So when you move away from f of x equals x squared or f of x and y equals x squared plus y squared, there are still ways of getting a grip on how the function behaves, but we no longer have a nice simple graph like a curve or a surface. So there's a little bit of vocabulary here, and then I'm going to try to work an example, a familiar example for you. If I look at a set in S in the domain of f, I can look at f of s, which seems kind of weird. I'm taking the whole set and I'm plugging it into f. Notationally, what that means is take every point in s and apply f to it, and then see what comes out. What comes out is another set. What does that set look like? How is it different from the set that you plugged in to f? And by looking at those differences, can we understand a little bit about how f behaves? That's such an important idea that it actually has a name. The image of S under F is what we get by taking every point in S, plugging it into F, and looking at the result. Similarly, if F, we can look at a set in the range of F and look at the collection of points in the domain that go to that set under F, and we can learn a little bit about F in that direction. It's two different directions. If I go from the domain to the range, I'm looking at the image of the set S, and if I take a set T over here in the range and I look at where it came from in the domain, this is the pre-image. We could spend weeks on this topic. In fact, I would love to spend weeks with you on this topic. It's a beautiful subject, and there's so much to learn here, and such a departure from the math that you've been exposed to up to this point in your lives. If you do have an interest in this kind of stuff, we do get to spend a semester doing a lot of this kind of work in complex variables, which I'll be teaching not next spring, but the following spring. So if you're still here at Whitman that following spring, look me up. I'd love to go through it with you. Okay, there are other questions that you can ask beyond how f changes the shape of some familiar object when we apply f to it. How does f change the area of a set? If I have a set over here in the domain and I look at its image over here in the range, how has the morphing and the twisting and so forth affected its area or its volume or its perimeter or its surface area? Right? These are all questions that mathematicians have explored and continue to explore. And Another huge area of study is, does F preserve other properties of a set? Like if the set over here is connected, is the set in the range connected? What do I mean by connected? If it's all of one piece, it's not in two separate pieces. So if it's all of one piece over here, is it still all of one piece over here in the range? Um, if it's an open set over here, is it still an open set over here? This gets into the subject of topology, a class that we teach infrequently here as a special topics, but again, I've taught that class, I love it, and if I can get a group of you interested in it, I'd be happy to offer it as a special topics while you're here. What's amazing about this is a lot of the questions that we ask like this are related to the derivative of f. But you might ask yourself, well, what is the derivative of a function that, say, goes from R2 to R2 or R3 to R3? It turns out that the derivative of a function from R2 to R2 is actually a 2 by 2 matrix. And from R3 to R3, it's a 3 by 3 matrix, an even bigger matrix. And so what this immediately leads to is the topic of linear algebra. Linear algebra is the study of vectors and matrices and solving linear systems. And there's a whole beautiful theory there that we won't get to touch in this class. But if you're interested in that kind of stuff, I would encourage you to go check out linear algebra. Integrals, of course, involve area and volume. And if we're going to be changing variables, we're essentially applying a transformation. And we need to extract information about that transformation so that we can properly convert the area in the domain to area in the range, or volume in the domain to volume in the range. And that's exactly what the factor r does in polar coordinates, and it's what the factor rho squared sine phi does in spherical coordinates. It tells me how volume changes under the spherical coordinate transformation. Let's go back to the textbook here and do a bit of a flyover. This is a review of U substitution. I'll leave that to you. Planar transformations are the two-dimensional version of this, and invariably what we get are two different copies of the plane. We have a UV plane on the left, which is the domain of the function, and an XY plane on the right, that's the codomain of the function. It's the plane that contains the range of the transformation. How does this work? Every point in the domain maps to some point in the range over here under this transformation. So I take the two coordinates u and v and I plug them into some mysterious function, and I get out the x coordinate and I plug it into this other mysterious function and I get the y coordinate, and then together that tells me that this point uv gets sent to this point xy over here in the codomain. This is R2 to R2, and we have an example of this. Let me see if I can, let me just slide over here. I have my little example note here. All right, so we have an example of this, the polar coordinate transformation. So I can get a copy of the UV plane over here and a copy of the XY plane over here. And remember the polar coordinate transformation. I'm going to use u and v instead of r and theta. X is equal to u cosine theta. Y is equal to u sine theta. And this is our transformation t. T of u and v is equal to the point x, y, which is equal to u cosine theta, u sine theta. So we're familiar with this. Let's look at a simple shape over here in the UV plane. Let's look at a rectangle where we go out to 1 in the u direction, and let's go up to pi over 2 in the v direction. Let's see if we can't figure out what happens to this set if we plug it into t and we plug every point into t and we see what that collection of points looks like over here. Plugging in every single point of this set would be a challenge, and it's a thing that you could do, but I don't encourage it. A better approach is to look at the boundaries of the set in turn and try to figure out what happens to the boundaries. So over here, along this boundary 1, what do we know about the points there? Along that boundary, v is equal to 0, and u is between 0 and 1. All right? So if v is equal to 0, apologies here, the transformation is u cosine v. V is playing the role of theta. Like that. Hopefully I won't make that mistake again. If v is 0, then under the transformation, x is equal to u cosine 0, 0, and v is equal to u sine 0. All right, well, that just works out to u and 0 as u goes from 0 to 1. Alrighty, so that means x goes from 0 to 1. Let's go out 4 here. And y is 0. So the image of the boundary labeled 1 is, let me draw it in a different color here. So the boundary of the red side is right there. Let's repeat this all the way around. Let's look at 2. Along 2, we see that u is equal to 1, and v goes from 0 to pi over 2. Let's see if we can't figure out what that looks like over here. That means that x is equal to 1 cosine v, and y is equal to 1 sine v. And v ranges from 0 to pi over 2. You might recognize this as tracing out the unit circle. This traces the unit circle. What part of the unit circle? It traces out the part of the unit circle for v from 0 to pi over 2. So that's an arc. So the blue side is going to go along an arc like this. And the angle here is pi over 2. Let's keep going. So that's side 2. What happens with side 3? Side 3. And it is, until you develop an intuition, it is pretty much this process of going through the boundaries. Along 3, the top, we have v is pi over 2, and u is between 0 and 1 again. All right, let's label, or let's color that side green, and let's see if we can't figure out what happens there. So repeating this process, looking at the transformation, we have x is equal to u cosine of pi over 2, aka 0, and y is u sine of pi over 2, which is just u. So what we see here is in the range, we're going to get the set of points 0 for x coordinates, and y is going to go from 0 to 1 because u is between 0 and 1. So if you haven't guessed it already, it's this side right here. And we're going to call that side 3, or label that side 3. Let's look at 4. 4 is a weird one. Along 4, what's happening? U is 0, and V is between 0 and pi over 2. Oops. Like that. Let's see what the x and y coordinates are doing. It's not a big leap to see that they're all 0, right? Because this factor of u that's in the transformation has a u in both of them, and u is 0. So, I don't know, we'll call it the rainbow side. What happens to the rainbow side? The whole side, that whole side goes to a single point. It goes to the origin. So let me label that as side 4, and I'll just make a note down here. All of side 4, we say maps to the origin under the transformation t. All of side 4 maps to 0 under the transformation t. And then what we get to do for free is we assume that the inside of the shape goes to the inside of the shape over here. And what we discover is the familiar shape in the domain of a square turns into a wedge shape under the polar coordinate transformation. And you can try this for other shapes, and I encourage you to do so. See what happens to other rectangles, for example. See if you can figure out what happens to a circle, although that's hard. All right. So that's what's going on there. And again, you might imagine that you can kind of see that the square, the left side of it got pinched to the origin. The right side of it got stretched out along this arc. So you can imagine that little pieces of area over here in the codomain, in the domain are going to kind of get stretched out maybe into bigger pieces over here in the range. And we're going to see how to figure that exact process out in a minute. So this is a more generic transformation. It's not the polar transformation, and this weird transformation takes this sort of square with rounded edges over to this sort of kidney bean shaped figure here. It's all completely abstract. No actual functions were used in the construction of that figure. All right. A transformation is said to be one-to-one if no 2 points map to the same image. You may remember this vocabulary from Calc 1 or maybe even earlier. This is the so-called vertical line test. This is the so-called horizontal line test. A function is one-to-one if it passes the horizontal line test. In other words, we don't have 2 different points in the domain going to the same point in the range. Let's go back to our polar example. Is the polar coordinate transformation one-to-one? Is this one-to-one? And the answer is a resounding no, because all of the points along side 4 go to the single point (0, 0). So this is a resounding no. Definitely not a one-to-one transformation. What does this mean for you and your children? Not a whole lot at this point in the game. It's just a chance to kind of learn a little bit of the vocabulary. As long as a function isn't too terribly failing the one-to-one test, it's still okay as a transformation to use in integration theory. And what do I actually mean by, not too bad? That's a subject for a different class. suffice to say that the polar coordinate transformation, which is clearly not one-to-one, is still an okay transformation to use when doing integrals, when changing variables in integrals. Okay, I know I'm talking a lot. Let's speed it up a little bit. The Jacobian is exactly the factor that tells us how area is changed when we go from the domain to the range. Here we have our friendly little set S and its image R under the transformation T. You can see that they have different shapes. Do they have different volumes? Probably. Generally speaking, transformations are going to change the volume of the set, or in this case, the area of the set that they act on. How exactly do they change that area? The book here goes through a derivation using the cross product to show you that this little formula is exactly the right number to use to scale the area. And it involves a bunch of partial derivatives. So remember, so you see partial x with respect to u, partial y with respect to v, etc. You're going to be handed a transformation, or you're going to come up with a transformation that looks like this. U is a function of u, x is a function of u and v, y is a function of u and v. So I can take the partial of x with respect to u, with respect to v, y with respect to u, y with respect to v. Those are all things that I can do. And if I mix them together in just this way that comes from the cross product identity, I get the Jacobian, and this turns out to be exactly the right number to include in your integral when you're changing variables. Just to see that, let's take this polar coordinate transformation and let's compute the Jacobian. So let's do the Jacobian of t. All right, the partial of x with respect to u, let's go up here and look at that. The partial of x with respect to u is cosine of v. The partial of x with respect to v is u minus sine v. And then continuing with the y variable, the partial of y with respect to u is the sine of v, and the partial of y with respect to v is u cosine of v. Now what happens is this is sort of like a little 2 by 2 matrix, and just like in the cross product, we can take what we call the determinant of this 2 by 2 matrix. Cross product. We can take the determinant of this and we get u cosine squared v minus negative u sine squared v, and that simplifies to u times cosine squared v plus sine squared v, which is just u because of the Pythagorean identity. Now I'm using u and v because that's what the book uses in this particular section, but if you were doing the polar coordinate transformation back in earlier sections, u is secretly r, v is secretly theta, and look at what pops out of here. The Jacobian is u, or r if we use r and theta instead of u and v. That's exactly the factor that we need for polar coordinates when we change an integral into polar coordinates or into cylindrical coordinates. This is the 2 by 2 case. If we carry on changing variables in the 2 by 2 case, here's the original variable and here's your change of variables. What you do is you replace the variables in the integrand with the transformation. So in other words, express x and y in terms of u and v. You include the Jacobian, and then you figure out what the preimage is of the set S under this transformation. Okay. We'll go through a number of examples so that you can see that. Let me just briefly talk about the problem-solving strategy here. You want to sketch the region in the xy plane. write the equations of the curves that form the boundary, and then either choose the transformation that works for you. We're de-emphasizing that in this section. I'm not going to be asking you to come up with transformations that work. I'm mostly going to be asking you to apply transformations that you've been given. Determine the new limits of integration in the UV plane, find the Jacobian, replace all the variables x and y in the integrand, and then carry out the integration. There's several examples of this. I want to jump over to triple integrals briefly before we get into the exercises. In triple integration, we lift this all up by adding another dimension. We have x, y, and z as functions of g, h, and k, each of which, as functions g, h, and k. Each of these functions have independent variables u, v, and w. So before we had x and y in terms of u and v, now we have x, y, and z in terms of u, v, and w. But the ideas are basically the same. You've got a set in the domain, and we plug all the points in that set into the function, and out comes some sort of transformation, twisted, shrunk, stretched, what have you, version of this set, and the volume is going to be changed somehow, generically speaking. How do we deal with the change in volume? The Jacobian. Now, the explanation that they used in the two-dimensional case that invoked the cross product and the parallelogram identity doesn't work here in 3 dimensions. And in fact, they're not even going to try to explain to you what's going on in 3 dimensions here. Instead, they're going to drop this 3x3 matrix of partial derivatives on you. Partial of x with respect to u, with respect to v, with respect to w, first column. Partial of y with respect to u, v, and w, z with respect to u, v, and w, right? This 3x3 matrix. And then you're asked to compute the determinant of this thing. And we'll talk about strategies for computing the determinant. Generally speaking, computing a 3x3 determinant is challenging. You may have seen this in other classes, but it's very prone to error. We're just going to keep the examples relatively simple, and as we go through the examples, I'll explain to you how to compute these determinants for triple integrals. All right, so when you see this notation, this is a 3x3 Jacobian. It means form the matrix of partial derivatives and then take the determinant. All right, there are a couple of examples here. I'll leave that to you to look at, and then we'll jump over and do a few examples from the end of our own selection. I'm going to pause here and I'll be right back. All right, let's switch over to the notes here and look at the first of these exercises. So in exercise 358, you're given a lot of instructions here. We're given a transformation T and a set S in the domain because we have U and V here, and U and V are in the domain. This is just a square of side length 1, and the image of S, R is the image of S under T. Justify that the function T is a C1 transformation. We didn't really talk about C1 transformations, but there's a brief description of what a C1 transformation is right underneath the section on Jacobians. It's sort of the first paragraph underneath the Jacobian section here. A C1 transformation is simply one where the component functions g and h have all of their partial derivatives and are continuous. Pretty much every function that we're working with in this textbook is going to satisfy that condition, so don't worry too much about that. So to answer the first part for this particular example, yes, this is a C1 transformation. So this is C1, yes, because all of the first partials exist and are continuous. And we can see that just by computing the partial derivatives here. So it's a good exercise, especially at this stage of the section. Let's compute those partial derivatives. The partial of x with respect to u, we look at this formula for x in terms of u and v, it's just 1. The partial of x with respect to v, negative 1. The partial of y with respect to u is 1. And the partial of y with respect to v is also 1. And in fact, we weren't asked to find the Jacobian here, but if you want to look at the Jacobian, we're talking about the determinant of this matrix. 1 times 1 minus 1 times negative 1 is 2. So that would be the Jacobian if we were using this transformation in an integration context. Find the images of the vertices of the unit square through the function t, meaning what happens when I plug the vertices of the unit square into the transformation t. Let's see that. So this is sort of building up to that visualization that I was talking about, where you have a simple set in the domain of the transformation uv. This is the domain of the transformation, and we have this simple set, just a square, and we're interested in the vertices of the square, 1, 1, 1, 0, 0, 1, and 0, 0. And we're going to just map the vertices under the transformation t and see where they end up. So let's see how this works. This is sort of like plotting a function way back in 8th grade by plugging in points. So let's plug in 0, 0. Where does 0, 0 go? So 0, 0 means u equals 0 and v equals 0. Plugging those in up here, we find that 0, 0, let's color code this just to be really clear. The red point at 0, 0 is going to go to the red point in the xy plane. Let's go around the set here. Let's look at the blue point, 1, 0. So 1, 0 means u is equal to 1 and v is equal to 0. So here, u is equal to 1, v is 0, x is equal to 1, u is equal to 1, v is equal to 0, y is equal to 1. So we get a point up here at 1, 1, a blue point. All right, let's keep going. Let's try a green point out here at 1, 1. All right, at 1, 1, and let me just add some labels here for those of you that might be a little bit colorblind. 0, 0, that's this point. And then this point goes, let me change that to blue. That goes here, and this is the point 1, 1. Okay, let's see where 1, 1 in the UV plane goes. So that means u is equal to 1 and v equals 1. That means x is 0 and y is 2. So we're going to plot the point x equals 0 and y equals 2. So that's way up here, and boy, my scale is somewhat unfortunate. 1, 2, 3, 4. So that point is way up here, and I don't know what's a good color. We've done blue. Let's do green. Yeah. So 1, 2, 3, 4. So there's the point 1, 1. Alrighty. And the last point, I don't know. Let's do rainbow color. So rainbow color, where does 0, 1 go? That means u is 0 and v is 1. Plugging those into the formula up here, we get -1 for x and 1 for y. So we want to plot the point -1, 1. So 1, 2, 3, 4. 1, 2, 3. Okay, there's -1, 1. Right, and that is where this point goes. Now, if you connect these dots, right, 0, 0, to 1, 1, to the green point, to the rainbow point, and back to the red point, what we get is a pretty good idea of how this simple unit square is transformed as you plug every point in the unit square into T and see where it comes out over here in the codomain. For what are these things called? For polygons. A polygon is straight lines that connect vertices, like a triangle, a square, a rectangle, a pentagon. Those are all polygons. For polygons, it's enough literally to just plot where the vertices go and then connect the dots and you're done. So polygons are really nice to work with when you're trying to visualize what these transformations are doing. Finally, we want to determine the image R of the unit square S and graph it. We kind of have done that. So this is R in the domain, and this is, oh, I'm sorry. This is S in the domain, and this is R in the codomain or in the range. All right, and we would say that R is the image of S under the transformation T. R is the image of S under T. So that's part C. And the graph is really part C. Alrighty, let's try another one here. So in the next exercise, we're asked to figure out whether the transformations are one-to-one or not. I'm not super interested in you figuring out questions like this. You should know what one-to-oneness is. Proving one-to-oneness can be a challenge. I chose this one because it's actually not one-to-one, and I'm going to just show you how it's not one-to-one so that you have a better idea of what this concept actually is. As usual, I want to get two planes, a UV plane and an XY plane. Labels are really important now. So that's the UV plane on the left, that's the XY plane on the right. Here's the formula for how points in the UV plane get sent over to points in the XY plane. S is in the domain, it's in the left-hand plane, and we're going to just plot these points. It's a triangle with these vertices, -2, 0, 2, 0, and finally 0, 2. That's the triangle. Okay. As I mentioned just a moment ago, this is a polygon. So it's enough to really just map the vertices and then connect the dots. So let's go around here and plot each of these vertices in turn, and we'll color code them so that you know that the blue one goes to the blue, green to green, red to red. And again, if you have color vision issues, just follow the arrows. I'll put some arrows in here in a moment. All right, so let's see where -2, 0 goes. We plug in -2 for U and 0 for V. Doing so, we get -2 to the 4th, which is going to be, what, 16? X is equal to 16, and Y is equal to 4. X is equal to 16, Y is equal to 4. We'll just put that right out here. We'll say each block is worth 4 units. So that ends up right there, and I want to make sure that that's blue. And that's the point 16, 4. And we'll draw the arrow in there. Right, so the point -2, 0 goes to the point 16, 4. Let's try 2, 0. So 2, 0, you plug in 2 for U and 0 for V, and look what happens. You get the same point. So I'll color half of this green, and this point actually goes to the same point. We immediately now know this is not a one-to-one transformation. Because these two different points in the domain end up at the same point in the range or the codomain. Just for the heck of it, let's sketch out the last point here. The red point, 0, 2, that means u is 0 and v is 2. So that's going to give me x equals 0 and y equals 2. And that's right about here in my units. So it's the point 0, 2. And I'll just connect it with an arrow like that. This is what we call a degenerate transformation. So it's not one-to-one, and plotting the vertices is not enough to figure out what the image of the set S looks like. This is the set S. We can't really figure it out just by connecting the dots, so we'd have to work harder. We're not asked to do that in this particular exercise, but if you want to practice doing that boundary analysis that I demonstrated earlier, you can do that and you can figure out what this set looks like over here in the codomain. We did answer the question, determine whether the transformation is one-to-one. This is not a one-to-one transformation because these 2 points in the domain go to the same point in the range. In this exercise 370, the transformations are both one-to-one. Find the inverse transformation. So if x is this function of u and v and y is this function of u and v, can you write u as a function of x and y and v as a function of x and y? And the answer is yes, and we're told that it's one-to-one, which means an inverse does exist. Let's look at this. This is essentially an algebra problem. We're trying to solve for u and v in terms of x and y. In the first equation, if we take the natural log of both sides, we get 2u plus v on the right-hand side. And in the second equation, if we take the natural log of both sides, we get natural log of y equals u minus v. Now we have 2 equations and a lot of unknowns. What's the goal here? The goal is to isolate u and then to isolate v if we can. I do see a path towards isolating u. If I add these 2 equations together, the v's will cancel. So adding the 2 equations, we get the natural log of x plus the natural log of y equals 3u, like that. And I can simplify this a little bit. The natural log of x plus the natural log of y is actually the natural log of x times y, and then dividing by 3, we've learned that u is equal to 1/3 x times y. So this is great news. We've found u in terms of x and y. What about v? Can we find v in terms of x and y? I think we can, because we can take this now and substitute. So we'll substitute this into the second equation up here. And what this will yield is the natural log of y equals 1/3 the natural log of xy minus v. And solving for v, we get 1/3 natural log of xy minus the natural log of y. And through this algebraic manipulation, we have actually isolated u in terms of x and y and v in terms of x and y. I'd love to tell you there's a recipe for doing this. Some of the algebraic skills that you've developed over the years will help here. Sometimes it takes a little bit of insight. It's like a bit of a puzzle. And just do your best when you encounter a problem like this. Okay, here we're asked to find the Jacobian transformation of the given, the Jacobian of the given transformation. This involves you creating that matrix of partial derivatives, but there's a big hitch here. This is a 3 by 3 system here. This is a three-dimensional transformation. So we have the variables x, y, and z in terms of u, v, and w. So let's start building that table of partial derivatives. The partial of x with respect to u is hyperbolic cosine of hyperbolic cosine of v. Partial x with respect to v is going to be u hyperbolic sine of v. And the partial of x with respect to w, there is no w in the expression, so that's 0. Keep building these columns. Partial y with respect to u is hyperbolic sine of v. Partial y with respect to v is u hyperbolic cosine of v. And partial u with respect to w, again, is 0 because there's no w in the expression for y. The last column, partial of z with respect to u, there's no u, 0. Partial of z with respect to v, there's no v, 0. Partial of z with respect to w is 1. Now, the matrix, the 3 by 3 matrix that we have to take the determinant of is sitting here in front of you. Some of you may have learned how to compute determinants by the method of cofactors in the past. I'm not going to dwell on that too much. I'll just show you by example here. So the method of cofactors is you pick a row or a column, any row, any column, and you work down the row. So I'm going to pick this column because it has a lot of zeros in it. And I'm going to block out, I'm going to go through each of the 3 entries in this column. So when I analyze the first entry, let's call this J, the first entry is going to be 0 times the determinant of the 2 by 2 matrix that I get by removing this row and this column. Doing that, I get the determinant of this 2 by 2 matrix, which you know how to do. It's the diagonal entries multiplied together and subtracted. Here we just get another 0, and so nothing interesting happens there. All right, so we get 0 times 0 for the first one. The second one always has a minus sign, so we'll put a minus sign in there, and then let's cross out its row and its column. And then we see a 2 by 2 matrix here, 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 here. And again, doing that cross multiplication, there's zeros down here. We just get another big fat 0. So you take the 0 here and the 0 from the determinant of the 2 by 2 submatrix, and you end up with another old 0 times 0. And last, and hopefully we'll get something non-zero here, the third element, we're going to block out its row and its column, and here we have a non-trivial 2 by 2 matrix. The hyperbolic cosine of v times u times hyperbolic cosine of v minus, and writing that all out, we get, let me get rid of these 2 red lines here. We get u, let me go back to black, u hyperbolic cosine of v squared plus u hyperbolic sine of v squared, like that. Sorry, minus, not plus, minus. This actually simplifies quite a lot. U times hyperbolic cosine squared, I got another meeting coming up here, plus, minus hyperbolic sine squared v. Now, you may or may not know this, but the hyperbolic trig functions have their own identities, and this is one of the identities. The hyperbolic cosine squared of v minus the hyperbolic sine squared of v is actually 1, and this simplifies to u. So the Jacobian of this transformation is u. All right, I'm going to pause there and go to my meeting, and then I will finish this up a little bit later. All right, in problem 394, we have a pretty classic example of a transformation or change of variables in two dimensions. We have this integrand, the square root of x squared plus 25y squared, which is going to be hard to integrate in Cartesian coordinates because we don't have any sort of accompanying du to do a u substitution. The book conveniently gives us a transformation that should be handy. And I'm going to go through sort of the process of visualizing this. This isn't always necessary, and you'll see this in a later example, but I kind of want to walk through all the pieces for you here. Now I know normally we have the XY plane on the right and the UV plane on the left, but this particular figure seems to require me to put the UV plane on the left. All right. So we're given this transformation. This is the transformation t. You plug in u and v and you get out x and y. So t is moving in this direction. It's taking points out of the uv plane on the right and sending them to points over here in the xy plane. The trick is to figure out, this is the region R. This is the image of some mysterious set over here in the UV plane. This S is the pre-image of R under T. How do we figure out what S looks like? Because ultimately, this integral, because it has x's and y's in it, this thing lives in the xy plane. This integral is occurring in the xy plane. And what we want to do is take this integral and through some magic make it an integral over s, some function of u and v dA over here in the uv plane. If we're going to do that, we've got to figure out what s looks like, the pre-image of r under t. Now, we're kind of lucky because we've been given the equation of the boundary of this figure in the xy plane. And if you take this transformation and you solve for x and y and you substitute it into this, you're going to get the boundary of the figure over in the UV plane, the boundary of S. So let's do that. We know that x squared plus 25y squared equals 1. We know from the transformation that x is equal to u and y is equal to 1/5 v. I just solved for y in terms of v there. Dropping those into this equation, what we find is u squared plus 25 times the quantity v over 5 squared equals 1. Conveniently, and actually not accidentally, the v over 5 squared turns into v squared over 25, and this simplifies to a very familiar equation. U squared plus v squared equals 1. And in fact, that's why this particular transformation was chosen, because the pre-image of R under T is just the unit circle. It's the unit circle. Now we know how to integrate the unit circle. We know how to integrate over the unit circle. It remains to kind of figure out what does the integrand look like in terms of u and v, and to figure out the Jacobian. If we're going to do the integral over here in uv space, we've got to include the Jacobian here, which I left out. All right, what is the Jacobian? The Jacobian is this matrix of first partial derivatives. The partial of x with respect to u is 1, with respect to v is 0. The partial of y with respect to v is, with respect to u is 0, and with respect to v is 1/5. Taking the cross product, the determinant, we get a Jacobian, a constant Jacobian 1/5. So that number has to be in there. Now, let's look at this integral. The integrand, the new integrand, in terms of u and v, is take x equals u, drop it in here, y equals 1/5 v, drop it in here, and you're going to get the square root of u squared plus v squared. So the new integrand is the square root of u squared plus v squared. So if we're going to do this integral, we need to integrate over the unit circle s, the square root of u squared plus v squared, 1/5 the Jacobian dA. All right. Now you're looking at this and you're like, you know what, Schuler, we have not solved the integration problem. I can't integrate the square root of u squared plus v squared, or at least not easily. And I say, au contraire, you can, because this is now an entirely independent problem. This is entirely independent of where we started over here. Now I'm asking you to integrate this function over the unit circle. Well, the best choice for that integration is, of course, polar coordinates. In polar coordinates, r goes from 0 to 1 and theta goes from 0 to 2 pi. So we should use polar coordinates to finish the job. And don't forget how polar coordinates work, right? To integrate over s, r needs to go from 0 to 1, theta needs to go from 0 to 2 pi. We need to convert the integrand to polar coordinates. The square root of u squared plus v squared is just r. The 1/5 goes along for the ride. And then what's dA in polar coordinates? It's r dr d theta. Now we have an integral that we can do. 1/5 integral from 0 to 2 pi. I'm not even going to bother. Integral from 0 to 2 pi, there's no theta here, so that's going to give us a factor of 2 pi. And then we need to integrate r squared from 0 to 1. R squared becomes r cubed over 3. Plug in 1, plug in 0, subtract, we get 1/3. Looks like we're going to get 2 pi over 15 if I've done my calculation correctly. You know, it was a long and winding path to get to 2 pi over 15. We started with this integral in the xy plane and this given transformation. We moved over to the UV plane, carefully computing the Jacobian and identifying the preimage S. And then once we converted to UV coordinates, we decided, hey, it's better to do this in polar coordinates, so we did another transformation. We dropped into polar coordinates, which we're more familiar with, and we ended up with a fairly straightforward integral. Definitely worth reviewing and seeing if you can do this example on your own. All right, in 104, I'm going to sort of even strip away more of the visualization and the interpretation of images and pre-images and so forth. We're given this triple integral in Cartesian coordinates, and we're given this transformation. U is x minus z, v is 3y, w is z over 2. Now, if you don't, right, I mean, you could try to figure out what this shape looks like in three-dimensional spaces, and it's actually not that hard, but I want to kind of get away from that because we're now sort of at the end of the section, and you've developed the intuition, and now I want to just give you a process. So the process is start converting all of these x, y, and z's into u's and v's using the transformation. So what is this going to look like? X is going from z to z plus 1, right? X is going from z to z plus 1. So let me get my notes here before I, where am I here? 394. Apologies here, hold on for a second. Okay, so let's express, let's solve for each of these variables in terms of u and v. This is often the case when you're working with a transformation. Not only do you need u in terms of the original variables, sorry, u, v, and w in terms of x, y, and z, but you need x, y, and z in terms of u, v, and w. We need it in both directions. So let's see if we can figure this out. We see, for example, that, oh, I don't know, let's do z. We see that z is equal to 2w. That's relatively straightforward. So now we have z in terms of u, v, and w, and there's only w. Similarly, we have y is equal to 1/3 v. So now we have y in terms of u, v, and w, but there's only v. The last one, more complicated, u is equal to x minus z. We're going to write u is equal to x minus, we know z in terms of u, v, and w, it's 2w. And so we can find that x is equal to u plus 2w. And again, checking my notes here, yeah, that looks good. All right, so this is the substitution. Now what I want you to do is two things. We have to convert this to the dv in triple integrals. We need j, the Jacobian. And we also need to convert the integrand, and we need to convert the limits of integration. All right, so let's start rewriting this integral in terms of u, v, and w. Y is just 1/3 v, and 1 is just a constant, so it goes along for the ride. We're going to need the Jacobian. We have z, y, and x now in terms of u, v, and w, so let's start building that matrix. The Jacobian is going to be the determinant of this 3×3 matrix. Partial of u with respect to u is 1, with respect to v is 0, and with respect to w is 2. Partial of y with respect to u is 0, with respect to v is, what, 1/3, and with respect to w is 0. And finally, the partial of z with respect to u is 0, v 0, w 2. We can compute this determinant by going along a row and using the method of cofactor expansions. Let's go along the top row here because 2 of the cofactors are 0. So all I need to do is write 1 times the determinant of this little 2×2 submatrix, which is 2/3. It's not important that I chose this one. I could have chosen 0, 0, 2 or 0, 1/3, 0. What is important is that I use a row or a column that has a lot of zeros. And so the first row was a good candidate. So the Jacobian here is 2/3. So I'll drop that in here, 2/3 dv. All right, let's figure out what the limits of integration are going to be. Z is equal to, where are we here? Z is equal to 2w. I'm going to pause here for a second. I need a drink. All right, we've got to choose an order of integration here in order to fill out these limits. So we're going to just arbitrarily choose du, dv, dw. Again, Fubini's theorem would let us do this in any way. Let's see if we can't figure out what the limits should be in the u direction in order to go from z to z plus 1. So if we look at that carefully here, we see that if u is 0 in this equation, then x equals z matches, right? Okay, let me back up. We're going dx, dy, dz, so that means x equals z to x equals z plus 1. That's the first integral. How do we copy that down here in terms of u? Well, if x is equal to z, what's u? It's 0. If x is equal to z plus 1, what's u? 1. So we've taken care of that first dx. Let's try to do dy by dealing with dv. Why did I choose this particular order? Because dv and y are just directly related to each other. So there are better choices than other choices, and you kind of get a feel for this as you do more problems. All right, so y goes from 1 to 2. So if y goes from 1 to 2, what does v do? Well, v must go from 3 times 1, 3, up to 3 times 2, 6. Last, z goes from 0 to 1. So if z is going from 0 to 1 and we want limits on w, what's w doing? It's going from 0 to 1/2. And that's the new integral. We've got all of the pieces. We've converted the integrand, we've included the Jacobian, we've converted the limits of integration, and we end up with this integral. You can do this one by hand, or you can jump over to Sage for the final answer. And indeed, a good exercise would be to do this integral in Sage, do this integral in Sage. You should get the same number. If you've done it correctly, you'll get the same number. Okay, the last one is a little bit more theoretical. You're given the transformation from R2 to R2, so this is a two-dimensional transformation, and it's a very famous transformation. It's called the rotation transformation, and it's if I have a couple of points in UV space, or if I have a point in UV space, what this will do, let's say here's the point in UV space. What this will do is rotate that point. The distance from the origin will be the same, but it'll rotate that point through an angle theta. So whatever, so here's the old one, right? What this will do is map this point to the rotation of through an angle theta around the origin. So it's very handy. This is a transformation that is useful in video games, for example, when you're generating scenes, you're moving around and so forth. These are all rotation matrices. And in fact, these formulas are so important that they are actually hardwired into modern graphics cards. Video games use these calculations so frequently that there are actual special chips on the graphics card that are designed to do sines and cosines and multiplications really quickly just for that purpose. So this point would have mapped to this point under the transformation t sub theta. And it's not just this theta, you know, you pick a theta and it gives you this rotation. All right, so we're asked to show that the inverse transformation of t sub theta is actually t sub minus theta. So this is an exercise in algebra more than anything else. Let's look at t sub minus theta. T sub minus theta, if we follow the formula up here, it looks like u of cosine minus theta minus v sine of minus theta. So what am I doing here? Everywhere I see a theta in the original formula, I'm replacing it with a minus theta. And u sine minus theta plus v cosine minus theta. All right, so that's what t sub minus theta looks like. And we know a little bit about how cosine interacts with minus signs. Cosine's an even function, so we can simplify this a bit. And sine is odd. So this minus sign disappears because cosine is even, and this minus sign can be pulled out because sine is odd. We pull it out, and this turns into a plus sign, and the first coordinate is a little bit simpler. In the second coordinate, we have minus u sine of theta plus v cosine of theta. All right. Now the real question is, how do we show that this is the actual inverse transformation? Well, if we take the output from t minus theta and plug it into t theta, we should get the original point. In other words, if I take uv and I plug it into t theta, right, I'm going to get this point, right? Plug it into t theta, I'm going to get this point. If I take this point and plug it into t minus theta, I should go back to where I came from. So let's see if that's the case. If that's the case, then we'll be able to say that t minus theta is the inverse of t theta. How do we check that? Let's check it algebraically. Let's plug u and v into t theta. What's going to come out of that is this expression. X equals u cosine theta minus v sine theta, y equals u sine theta, v cosine theta. So we know that t theta of u and v is equal to u cosine theta minus v sine theta, u sine theta plus v cosine theta, right? That's the coordinates of the point over in x, y space. All right, well, if we take that now and plug it into t inverse, what's going to happen? All right, well, plugging that into t inverse, this is going to be a little bit confusing with the variables here, but you know, technically t inverse of theta should use independent variables x and y, because t inverse takes x and y and produces something over here. So I'm going to rewrite this as x cosine theta plus y sine theta minus x sine theta plus y cosine theta. This is x, this is y. Let's plug in this expression everywhere we see an x, and plug in this expression everywhere we see a y, and let's see what happens. All right, so let's take that t inverse, sorry, t negative theta, t of negative theta of x and y looks like this. It's going to be a long expression. X is going to be u cosine theta minus v sine theta times cosine theta plus, now we take y, u sine theta plus v cosine theta, that's y, times sine of theta, comma, we're not done yet, minus x u cosine theta minus v sine theta, and then sine theta, plus take y, u sine theta plus v cosine theta times cosine theta. All right. Wow, that's a lot of stuff there, but that's what we get by plugging x and y in. Now we should simplify. All right, let's simplify this. We see a minus v sine theta cosine theta and a plus v cosine theta sine theta. So this bit is going to go away and this bit's going to go away. What's left behind is u cosine squared plus u sine squared, and we recognize that as just u. Let's look at the y coordinate now, or the second coordinate. In the second coordinate, we have minus u cosine theta sine theta plus u sine theta cosine theta. So these are going to cancel. They're going to go away. What's left is plus v sine squared plus v cosine squared, and that simplifies to v. So this point goes back to where it came from, and therefore we can conclude that t inverse theta is actually, sorry, t negative theta is actually t inverse of theta. And there's the proof. All right. Suggested exercises. I want you to de-emphasize 388, 389, 398, 401. Why? Because in these exercises, you're being asked to find a transformation that works, and that's a little bit beyond where I want to go with this particular section. Um, the main reason I've done this is to kind of expose you to some more abstract mathematics and to show you that there's more to life than calculus. You know, the math department here isn't just Calc 1, Calc 2, Calc 3, Calc 4, Calc 5, Calc 6, Calc 7. It doesn't work like that. Once we get past Calc 3, the math sort of branches out and gets into all kinds of different subjects and really interesting and very different from calculus. Um, Similarly, 408, 411, 414, and 415, you're being asked to visualize, you're being asked to like look at sets and images of sets and pre-images and so forth. And you can do all of that. You can plot all of that in Sage, and I'm happy to work with you individually if you're interested in doing that kind of work. But it's not something that I'm going to emphasize in this class. Time is short, and we're just going to move on. This is motivating the RD theta, the rho squared sine phi d rho d phi d theta things that you've been dealing with for the last week or so. This kind of puts it all in a nice little bundle and points at kind of the deeper theory, but we don't have the time to get into the deeper theory. All right, when you've worked on the other exercises that I haven't mentioned here and you feel like you're ready, jump over to WebWork and look for Chapter 5, Section 7, and see if you can't get the assessment done. Thanks a lot. See you soon.